I'm so pleased that so many of you showed up this morning. I know at the end of a long trip in Las Vegas, it's very tempting to sleep in, and I hope you're still enjoying your nights out. I know my wife's here with me on this trip, and I know I'm enjoying myself. And although it's a little bit hard on us, we try to watch our health, and it's so heavy, so much heavy, salty food. It's really hard. But we've been checking our weight, weighing ourselves as we check our health here throughout the week. And what's been bothersome to me is that I couldn't understand why I haven't been gaining any weight. I weigh myself every day, and the scale is not going up. And I kept wondering about this conundrum day after day, and then finally I realized it's because my wallet is getting lighter every day. So that's why there must be an equilibrium there between the weight I gain here and the weight I lose here. So let's talk about another kind of weight management, really, right? Inventory, work in progress, these are essentially items of weight management for a firm. We're interested in controlling this workflow. We're interested in controlling this weight of the enterprise, managing the weight of the enterprise. So let's take a look here. What is workflow control is what we're going to talk about. I'm going to have a couple of slides on that. We talk about workflow control. Then I'm going to define in the academic literature what specific methods of workflow control are. I have a couple of slides to show you on that. Then I'll show you how I model these things in Arena. I have a couple of slides, and I've also got some sample Arena models I can show you. And I'll bring to your attention a specific problem that does exist called lockup, where systems can come to a crash and halt if the workflow control method is not implemented correctly. And I'll demonstrate that also with the slides and with an Arena model. So let's get started here. I want to find out what you all are all about here. How many have been using Arena for more than 2 years? More than 5 years? Okay, so it's an interesting distribution there. How many of you all know what the C's module is? How many of you know what the C's module is? Okay, so we got some experienced users. Release module, you probably know what that is too. Batching module. How many of you use batching module? Okay, you know what batching is. So we got some relatively skilled users here, and a match module. You can hear using match. Okay, so everybody here is, a large number of people here are fairly skilled users. That's great, so we won't have a lot of difficulty with that. Let's talk about workflow control. What defines workflow control? We're fundamentally interested in two categories of shop management. One is called push, one is called pull. Some of the things I'm going to say in defining these terms are going to be counterintuitive and different from what some of you have learned. Primarily because, quite honestly, there's a certain group of us in academia who believe what you've learned is wrong. Push and pull are not, as some of you may have been taught, related to whether or not it's make to order or make to stock, or whether or not it's driven by the customer or not driven by the customer. Those definitions, if you follow them, quickly lead to a situation where the terms are vague and suddenly the definition of the shop becomes unworkable. Those terms fundamentally should be defined as, do you have a fixed rule for controlling shop work in progress? Do you have a fixed rule for controlling inventory, or do you not? If you have a fixed method, an enforced limit on work in progress, on inventory, then that is by definition a pull system. And it has nothing to do with whether it's make to order or make to stock, or whether you listen to what your customer is telling you or you ignore what your customer is telling you altogether. If you have an enforcement rule that says we must not have any more than X number of units of material in this zone, that is a pull system, period, without any further enumeration. If you do not have such a mechanism, then that would be a push system. Now, within a pull system, we're going to look at two dominant schemes. One's called Conwip, one's called Kanban. I'll define those in more detail here in the next few slides. Here's a little matrix to try to put this what I've just defined for you into context. We have here push and pull at the bottom of the scale, and we have make to order and make to stock at the left-hand side of the scale. And I've picked some types of activities, some of them perhaps a little bit fanciful or hypothetical, but I tried to pick something that would really clarify what the intersection of these terms are. So, for example, the Toyota production system, which in most textbooks is frequently attributed to be a pull system, and it is a pull system, is a make-to-stock system because they make cars to inventory. They hold an inventory of cars at the dealer, They hold an inventory of cars for distribution, and customers buy from that inventory. And they use a pull system to fundamentally limit at every stage of the production line the quantity of items in that zone. The quantity of items in inventory, the quantity of items in work in progress. They have a pull system that limits that inventory. On the other hand, a lot of industries such as agriculture, petroleum, the liquor industry, these do not have, very rarely have inventory limits. Sometimes because it's impossible to have an inventory limit. In agriculture, you are completely at the whim of the weather and God, and your inventory is a matter of what was the crop that year. And some years the crop is really good, and you have a lot of inventory, and you just got to suck it up and take it all in. You can't do anything about it. But you are made to stock. You make grain and corn to inventory. You put it in a silo, and then the customer buys from that inventory as time moves through the year. You make strawberries and raspberries, and then you put them in cold storage, and you sell them through the season. You process them, you store them in various ways. Petroleum industry is notorious for inventory because people treat petroleum as an investable commodity. They buy petroleum and store it somewhere hoping the price will go up in the future. So by definition, petroleum has enormous amounts of inventory all over the place. So people do not specifically try to control how much inventory of petroleum they have because they're in some cases intentionally hoarding petroleum in order to work the stock market or to work the economic financial market. Then we go up to make to order, right? An a la carte restaurant. The restaurants here at Caesars. They are making to order. The customer comes in and asks the restaurant cook to make something. There is no inventory system that limits the chef in the kitchen from making any particular food item. If 30 people come in at once and they all want spaghetti bolognese, that chef is going to start making a lot of spaghetti. And he's not going to stop and say, oh, wait a minute, I have an inventory limit, I can't make that much spaghetti. He's not going to do that. That's a push system. Make to order and a push system. On the other hand, elective surgery. Very definitely a pull system. There are only so many beds in the hospital. There is a fundamental fixed inventory limit on the number of people that can be in that hospital on any day receiving elective surgery. That is, by definition, a pull system, firmly enforced by the limited number of beds in that hospital. And it is made to order. People come in and request surgery. Maybe they make a reservation in advance, but they request that surgery. It's customized to each customer. So you can see, and you can imagine in your head any type of business, maybe your own business, and walk through these decision models and say, am I push, am I pull, am I made to order, am I made to stop? And you have this 4-zone matrix here that defines all of these categories. So clearly push and pull are not dependent on what your relationship with your customer is and what your business model is. They're dependent on other factors. The way in which your product is made, the way in which you strategize in terms of how you hold and store product and deal with the marketplace. So let's talk about pull systems. We're going to really talk about pull systems now. If you're having a push system, then none of this applies. None of these next slides are going to apply. If you have a push system, you just don't do anything. You just let it go, let it ride the waves, and live with it. But if you want a pull system, you have to figure out ways to implement some kind of control system to limit inventory. Well, let's stop and say, why would we do this? Why would we want to limit this? Well, if you limit inventory in the system, generally, you will see a shorter flow time. Things will move through the system faster because Little's law, by definition, you reduce the inventory, then the transit time through the system is going to drop. And you usually, many firms have an enforcement limit on inventory because they're looking to reduce their return for their investment capital. They're looking to reduce the amount of money and funds they have invested in assets in the firm. So you reduce your investment. However, there are hazards. The more you push to reduce inventory, the higher the hazard of stocking out, and the higher the probability that you'll have a backlog in a make-to-order environment. So in a make-to-stock environment, the hazard is stocking out, failing to have inventory to serve the customer. In a make-to-order environment, the hazard is that because you're holding down inventory on the shop floor, you hold back orders that you need to start on a make-to-order basis, and therefore you have a larger backlog of work that has not started yet because your inventory control system refuses to allow that work to enter the shop floor. So those are the trade-offs, those are the hazards by implementing a workflow control system. Let's define these fundamental workflow control methods. First basic one is called Conwip, consolidated work in progress. You have one zone of control for the whole enterprise, and you hold the amount of work or inventory or product in that zone to a limit, to an upper limit, and you implement some kind of management system. The textbook method is a set of cards, where you have a card representing one unit of inventory, and you say there's only so many cards, and you can't have product on the shop floor unless you have one of these cards with the product. In this modern world, we can do this with databases as well, obviously. You don't have to have a physical card. You can have a database system. You can track things by serial number, by SKU. You can have decision rules that say work is not allowed to proceed unless the inventory level reaches a certain point in our database. So let's look at this Conwip system. Most of you are probably familiar with what this diagram says, but let me just review what we're looking at here. We have a flow of materials or products or work through this system from left to right. A is some work going on. K subscript A is a queue, is inventory. B is some work going on. K subscript B is another queue with some inventory. And then C is some work going on, and then we're out of the system. This black thing down here is the loop of our inventory control system, of our workflow control system, of our cards. The solid line is where we are controlling inventory, and the dotted line is the control signal looping back to the front of the cycle again. So in a Conwip system, we have a card attached to our work throughout its journey through the zone of control, which in this case extends from A to K subscript B. So we have our card attached, we have a free card recirculating, and the inventory limit in this system can never be more than the total of the number of cards, in which case we're going to call K subscript A and K subscript B as our total inventory limits right there. So we'll have a Conwip card count, and we cannot have any more inventory than that. It looks kind of like this. So at rest, let's imagine this system with 10 cards. This is a make to stock system, so we have allowed material product to consolidate at the bottom of at the end of the chain here, and we're waiting for the customer to come consume or purchase something from our stock. Customer comes and buys something from stock, pulls something from stock, and the card is now released from that item. And the card recirculates around the front, where we are then allowed to restock. We're allowed to reinitiate a new production line, run parts through this thing, and refill our inventory, and we're back to rest again. So it's a Conwip system where the cards recirculate. Now let's get Kanban. Kanban, we want to divide our inventory control up into zones. So in Conwip, we say one big zone for everything. In Kanban, we say, we would like to have a little finer control on this. We would like to have separate control for separate zones. So now we have divided that previous model into two zones, and we now have two card loops. Now to get the same relative inventory level as the previous system, we need to divide that previous card count in two. To get two zones, we divide that in two, so we now have two card loops. Same whip limit, but now we have 5 cards in each loop. So now it also causes us to now distribute that inventory. Instead of the inventory sliding to the end of the circuit, we now distribute it evenly throughout the system. So now we have 2 card loops going here, like that. There we go. So how do we model this in Arena? Let's talk about how to model this in Arena. A Conwip system is these days. No problem. No big deal. You simply say, okay, I'm going to set up cards as another resource in my system. And I'm going to limit the number of cards. I'm going to set a resource count in Arena for something called a card. Set it to some fixed number. And then tell my model that when I arrive to the zone of control, the red is my zone of control here. When I come into the zone of control, I can't go any further until I get a card. So stuff stacks up. I wait for a card. I get that card, and then I'm allowed to go in. And I go through my processes, and then when I leave the zone, I release that card. Cards are now released to free resources in Arena, and I start that circle all over again. Very simple, not too hard. This is a make-to-order Conwip system, which is the simplest most basic model you can do in Arena. Doing this in make to stock gets more complicated. So now we're going to do Kanban, and we'll see all these models here. We'll go to the Arena system and see these models soon. Now we go to Kanban. Things get a little messier when you're trying to do make to stock because you get a little trickier in doing things. So in make to stock, what I do is I treat the product cycle as this kind of closed loop that just recirculates all the time. And all it does is serve as a timing loop to emulate this process of manufacturing product. And then I have my random customer stream over here, where a random customer arrives and comes down here to this purchase cycle and says, I'd like to purchase something. And then when anybody guess which module am I using right here? This purchase box, what module am I using right there? Anybody have a guess? It's a match, right? So that's a match module. So the match module works here. I have product that's stacked up in the match module with inventory at the end of the cycle. Customer comes along and I've set this thing to say, okay, match one customer to one piece of product and out the door they go. Customer goes out this way, but my product is free to recirculate back to the system again and reinitiate this production cycle. And so what I do in this model is however many cards or however, whatever my dimension of my inventory level is that I dimension for my card system, that becomes the initialization routine up here where I set how many entities I flow into that system at the very beginning of the simulation cycle. Let's talk about a little tricky bit here though. If you're doing make to order Kanban, make to order Kanban system, and particularly if you have a very complicated routing where there are different types of products that have random routings that go, you have say a job shop, different processing machines. And in a job shop, product can move to a different sequence of machines depending on the unique characterization of that product, and very often that characterization is random or semi-random, has a lot of variability. There is a risk of something called lockup. Lockup occurs, and this is the most basic example of lockup here in this slide. Lockup occurs when you have two work centers, A and B, each of which has the queue of waiting stuff at the beginning to go into the work center, which is waiting to get a card to get permission to go into that work center. And there's a limited number of cards for each work center. And however, in a Kanban system, in make to order, the way we have to work this is we cannot, in order to enforce the work limit, in order to enforce the inventory limit, you cannot release your prior card until you receive the next card. There is a handoff. It's a relay race. There's a handoff on the token. Because if you release the prior card first, there would be this gap in between where there would be no inventory control, and suddenly there would be this free zone where there would be inventory piling up that was not under any control mechanism. So there has to be a handoff where you get the next card before you let go of the previous card you're holding. However, in this picture right here, if we have 3 cards for each loop, and I have 3 things here waiting for a card and holding the prior card, and 3 things here waiting for a card and holding the prior card, they can't go forward. We're in lockup. There is no way to move forward because they are all holding the resources that the other needs to move forward, and nobody's going to make a trade on their own initiative. It's not going to happen. So we have to have a mechanism that checks for this and unlocks it and frees it up. We have to have a mechanism that will free this up. And I do that here in this system. So here's a make-to-order job shop Kanban system. And in this system, I am randomizing the route. I have 2 work centers, but the probability, the jobs come in and they randomly go to one work center or the other first, and every time they exit a work center, there's a random probability that they are done. And I at the top of my head at the moment, I can't remember exactly what the percentages are. We can look at it. It was just an experimental model, but it's something like 25% probability of exit at the end of each machine, and 75% probability to keep on going. Which means for some finite number of jobs, for some hypothetical number of jobs, they never exit, right? Some minuscule probability that some job never ever leaves the system, but that in arena world, that doesn't happen. It eventually gets out somewhere. So we have this system up here, and what you don't see in this slide because I couldn't fit in the slide. I think I've got it on the next slide. Here we go. I zoom out now. So that was in the system, but down below we have our release mechanism for lockup. And I'll show you this in the arena model. After we get to this slide, I'll pull up the arena model and we'll take a look at the model. Down here at the bottom, we have something called a safety card. We have a reserve card called a safety card. It's initialized in the system at startup. It just initializes and goes straight to a hold module. It just sits there at a hold module. Up here at the cards, at the seize modules for the cards, instead of setting up my cards as flat resources at the seize module, I set up sets, resource sets. So each of the seize modules, instead of seizing card A or card B, is seizing a set composed of card A and the safety card. And so under normal operation, the safety card is held down here. It's held up. It can't go anywhere. It's occupied with this entity down here, seizes it, holds it in the hold module. And under normal operation, this thing chugs along using just the cards that are provided. But down here at the hold module, I have control logic that says, if all the resources are occupied and the machine is idle, release this card. If all the resources, all the card resources are occupied, and yet I check the utilization of the machine itself, the machine resource is not occupied, clearly we're in lockup, because it doesn't make any sense. I can't have all the resources occupied in the cards and yet have no production going on. Clearly the system must be in lockup. And that triggers this to release. That frees this resource for one cycle. This entity loops back around and immediately grabs it with priority as soon as it's available again. So we don't let the safety card run free very long. We just let it go long enough to unloosen this system, to unlock it and let it go again. And that, I think, is a good point for me to switch over to the arena model. I'm going to assume, judging by the high skill set here, so here's our Conwip model. This doesn't require any discussion. This doesn't require any conversation. Everybody, I think it's pretty clear. This is a pretty easy one. Make to order Conwip, that one's pretty straightforward. Then we have see if I can get this into the, this window a little bit. There we go. All right. Then we have our make to stock Kanban system here. And I'll just kind of run that for a couple of seconds. I think everybody's pretty clear now. This one works too. Just speed it up a little bit. No one has to talk about it. So that's pretty straightforward. Are there any questions? I think most of you probably have an idea how this was working, but if there are any questions, I'd be happy to answer them. This one's pretty straightforward. We have our match module. People are coming in and waiting. Those are customers waiting, and then the green dots are product. So sometimes the customer waits, and sometimes the product waits. Depends on the settings you have for your model. I'll stop that. Get to the meat of this thing. Let's get to the one with the lock up here. Let me move this guy down so we have a bigger window to view. There we go. So here is our make to order Kanban system right here. And we have random routing here, and let's see, I'm just curious to remember what I had this set. Yeah, 50%. So I got 50% chance of going one way or the other. And then I come around up here and I seize my card. There we go. Seize my card, and there's a Kanban card right there. There we go. Get that mouse to work. All right, going around the loop here. And then I've got checking for my safety here and doing all this stuff. Let's see, where's my control? I'll bring it down. There we go. And here is my pull object. I'm checking. That's too hard to get in there. I'm checking for my queue. My queue gets too big. I've got a couple different versions of this. I've actually got 3 different versions of this control object, and I've tried them all. This is version 3. I've got 2 other versions on the computer here. I've tried different ways, but this will run. And everything's fine, we don't have a problem, we don't have a problem, but at a certain point, wham, every time we hit a lockup, that's when that's getting triggered down there. And I had a couple, I mentioned I had a couple other versions of this. Let me see if I've got those different conditions. There we go. That one. This one got messy. I didn't like that one much. Let's go right here. Here we go. These. Well, that one has a different card limit. That's what that one. Been experimenting with these, even in my own time. I've been experimenting with these different models. But generally, that's something you have to be concerned with. So if you're doing a make-to-order and a Kanban system, you have these random routings. You've got to be careful about the lockup, because if we turn this lockup off, if we turn this off completely, I could do that like this. I could do, let's see. I could just turn this off completely. I could hold this forever. Condition. See, I want to make this never happen. So that's never going to happen. We're done. Take the safety card out. We're in lockup. The system's in lockup right now. We have all 8. I guess I had this set. I can't remember if I got 8 or not. 8. It was 8 because it was 16 in that other dialogue. 8 safety cards, 8 Kanban cards in this loop, 8 Kanban cards in that loop. All 8 are occupied here. All 8 are occupied there. Nobody can move forward because this guy needs that card to move forward, and that guy needs this card to move forward, and we're done. We're frozen solid. And the thing is just going to sit here and churn away forever and ever. So that safety, that whole lockup thing is a real issue. Now in the real world,
what's that statistic that you had down there? Is that the number of lockouts?
At the very bottom, yeah.
Why is it jumping so much?
I think.
Is it just moving so fast, or is there?
Yeah, it's moving fast.
Okay.
Yeah, for example.
It does 4 at a time.
Yeah, it was jumping, and it also. I have to admit, I've been tinkering with the control logic, and I keep messing with it, and every time I mess with it, I get a new operating scenario. But right over here, let's double check the number of seizes. Now, I'll tell you why also, because when the safety card goes out, right, it gets seized once to unlock the system, and then when it's done unlocking the system, it gets seized again to go back into storage. So each cycle of a lock is 2 seizes. So we're going to have a 2 jump minimum, just every time it's used. And if for whatever reason it gets done twice in a row, then that would be 4. So it's going to always be multiples of 2. Yeah, it's going to jump in multiples of 2. So let's see. get back the way it was. Yeah, it'll jump in multiples of 2, and in fact, if I do this really slow, what was my train of thought? So, safety cards, got to have that. Oh, I was going to say in the real world, right? In a real shop floor, somebody, a human, would eventually realize what was going on, hopefully, and say, "Whoa, wait a minute," and somebody would override, manager would override. Well, you got to move that forward, or a runner would run back and forth between 2 places and switch the cards manually. But obviously, your simulation model can't do that for you. So you do need this control logic in your simulation model, even if in the real world, the guys can just figure it out and just solve the problem all by themselves. So it's something to be aware of when you're modeling these kinds of systems, these kinds of control systems. I have hypothesized, though, that in an intense manufacturing environment, a very large enterprise, this might actually happen because they're all database-centric, or the enterprise is so large it's not communicating with each other. And hypothetically, in a large enterprise, I can see this logic happening in the real world, too, unless the management is aware of it and looking for it. I can see a couple of work centers shutting down for at least 16 hours or something until management wakes up and realizes why those work centers were shut down. Questions? Any other questions?
Is it possible that you could be releasing those safety cards? You have all 16, you have 16 items in process, and then maybe both leaders should get released at the same time, just from finishing the process, and then they could just get released.
Yeah, I've tinkered with this control logic, and I suppose this is where we start stepping off into custom module development or VBA or something. It's kind of tricky with the timing. And I try to keep it simple, basically, fundamentally, because I have to teach this to students at the university, and so I want to keep the tools that I use very basic. I want to avoid being too complicated. But the reason I have so many versions of this is I had to experiment with things that responded the way I wanted to, but didn't respond, like you said, too erratic, too touchy, too quickly. And also, sometimes the way in which I sequence the steps, Arena's control logic doesn't catch it when I want it to, and then it fails to address the lockup. So I sit there and tinker with it, and so there's a little bit of experimentation that you have to stop and step through this in slow motion as you're testing your model to see if Arena is working the process steps in the sequence you think it should in order to catch your lockup and to respond properly. Because I experimented with all kinds of things. I experimented with as I said earlier in the lecture, I experimented with testing the status of the machines, and that worked sometimes, but I was finding situations where Arena wouldn't run its control logic and catch that at the right moment. So I settled at this particular version right here, I settled on just a random, just a mandatory, when all 16 are in use, run the safety card. It's a little bit heavy-handed, but it keeps the lockup from happening. Ideally, I would want it to be stricter. I would want it to be 16 cards. 16 cards or 8 cards are occupied in one loop and the machine is idle, and then release the safety card. But I found in some versions when I'm trying that with the Arena that I couldn't get the logic to be exactly the way I wanted it to. It wouldn't catch it. And rather than fool around with it much longer, I just quit. So fine, it's good enough for lecture. I'm just going to do it. But I'm sure with more tinkering and control logic, that should be addressed. And then it all also has to be unique to your enterprise too, right? So what is the business rule at your enterprise that says, here's how we'll address lockup, here's how we'll respond to it? Is it? And there might be other reasons besides lockup for a safety card. There could also be an argument that says we want to increase, even though we're not in lockup, if a machine is idle and there's work waiting for that machine, we would like to increase the number of parts and allow that machine to start working. So that's another reason that safety car is just to override the inventory limit when certain business conditions say, yes, my inventory is at its limit, but no, I need to utilize the machine. Let's override and go forward. So there are lots of different scenarios where you can say, gee, we should have an override. We should have a limit.
Also, real quick, in your example here, you have two processes on there. They look like they can run parallel, correct? You have two parties.
These are two separate work centers.
Are they doing the same thing?
They're imaginary exponential processing times of some academic topic, and work is randomly routed up and down. And then when they exit those machines, they are randomly routed either to exit or to the other machine. So it's a 50-50 chance of which machine you're going to go to first. And then after that, it's like a 50-50 chance of I'm out of the system or I'm going to the other machine. And it's a two-machine system, so it's really simple. I've done research, not with Arena, with another simulation system a couple of years ago where we used kind of a standard academic paper uses a 5-machine job shop. For some reason, 5 machines is like the standard. Mainly because it's a nice number. It's complicated enough to develop complicated questions, but it's not so complicated that you have this enormous programming investment to get the answers out. So 5 machines tends to be every research paper in job shops says, okay, we got a 5-machine job shop. And there's a fancy name for that actually. It's called the Jackson Network. The Jackson Network of machines. And the idea is that the exit from each machine then is either some percent randomly routed to exit, and then the remainder percent evenly distributed to the other 4 machines. And then you do this endless loop where there's an exponential curve of how long does that job stay in the shop before it's out the door. So we've been racking up, as I sped it up, we've been racking up safety cards. Yeah, and there's a 2-card jump. Yeah, so that's the number of seizes, so every time it seizes, it's a 2-per. It's once to unlock, and the second time back into its holding cycle. So to review, I really appreciate your time and attention here. Pull is implemented using a Conwip or a Kanban system, which are common textbook methods for doing this. We can model these things in Arena. Some are easy, some require a lot of finesse. Job shop environment, make to order, random routings. You need to be careful about lockup. It can be a real factor, and you can consider it in your Arena model and have some mechanism to respond to it. You can have a standoff where 2 machines or more machines are all both trying to get the same resources, and yet those resources are being held by other jobs that need other resources to move on, and so nothing happens until you find a way to unlock all that. And in the academic literature, we call these safety cards. We have this thing called a safety card, and we use that to unlock this cycle. And there are various ways of implementing these safety cards. I've got these model samples online. Here's the web address. You can pull those down, and I really appreciate your time and have enjoyed your questions. Thank you very much.